Okay, so talking about the change in the grading a little bit. So I was going to give you a midterm project for you to do to work on a data set that you could bring from your own research if you had this type of data set to do a full experimental design analysis as that project. I am making a small change to that. So the change is we're not going to have that midterm project. We're going to have a final project that you're going to be able to choose if you want your final project to be about experimental design or about machine learning. So you can choose that whichever type of analysis you would like to conduct. Um, if you do based on experimental design, it would be something that comes from your research. So you're going to bring the data set, you're going to analyze it, you're going to go through all the steps that we learn in class, and that's going to be coming mostly from you, right? So the data is coming from your side. If you don't want to do that, you want to do the machine learning project instead, my goal is I'm going to give the class a couple of different data sets so it matches a little bit more the different areas of expertise we have here. So we're going to have one data set that's going to be like field level crop response of some sort, and another data set it's going to be more food science related, so it's more applicable to you, with the goal of training different machine learning models and making a prediction on some variable that you're interested on, right? So two different types of analysis. And in this case, the machine learning is going to be two different types of data sets depending on your area of expertise. If you do decide to go with the machine learning one, I think it's at least I think it's going to be more fun because there is a competition aspect to it. So we're all going to be getting the same data set, and then you're going to be tasked to see who can make the best predictions based on some metrics that we're going to learn about. In which case, I mean, everybody's going to be graded equally, and everybody can get 100%, but only one person or team is going to be the best model, right? So that team, that person may get some small rewards or awards for that from the class. So there's gonna be a competition aspect to it that is not going to happen on the experimental design part of it. Anyways, I just wanted to give that quick update because I know it was a question that Shakir brought up and I didn't have time to cover this last class. So it's just one final project. You can choose if it's going to be for you experimental design focused or machine learning focused, and that's going to be it.
Dr. Vestas,
Yes.
so will there be any final exam? Because the syllabus doesn't say there will be a final exam.
Yeah, so there may be, and I'm saying there may be just because I think it's going to depend on how grades are going this semester overall. We may have a final exam. So I mean, this right now we don't have one in the grading criteria, but it may change, and if it changes, I will let you all know way beforehand. So you have time to prepare. Yeah. Okay. All right, so let's begin with today's exercise. I share with you two new files, so a data set and a script. I asked you to create a GitHub. Yes.
Sorry, do you know what would be the final percentage for the final project?
I have to go back and revisit that, so I don't know yet, but I can tell you all on Thursday. Yeah. Yeah, so Priscilla was asking about the percent of the final project, so I'm gonna revisit that and let you all know next class. Okay, so for today's exercise, I asked you all to start off that GitHub workflow on your side for an exercise called 09 Open Data. So I'm assuming that you all were able to do it, and then we're gonna get started with that exercise. So if you want to launch that project, please go ahead and do that. I'm going to do that on my side here. Just make sure you have the correct project and launch that script, and we're going to get started. All right, so yes. Sorry, can you say that again? Which data?
Yeah.
It's the cotton field data. Yeah. Yeah, so the data set, just to let you know, is the cotton field data.csv. All right, so part of data science at large is to be able to find open source data that is relatable and important for whatever you are studying. So that's what this exercise is going to be focused on. In this case specifically, we're going to be working with weather data that's going to be variable both in time and space. And this is especially important if you have studies that are happening out on the field. So if you have a crop growing or something you're evaluating, it's an open field that is subjected to weather in this case specifically, right? And that you have the GPS coordinates of that field location. This is also important for this specific exercise. In agriculture, there's a lot of different open source databases that we can leverage. Those include things like crop databases. For example, USDA NASS, National Agricultural Statistical Service, has so much data about crops that is just amazing. We have data related to soils. So we have SIRGO, we have the Soil Web Survey, that we can pull those data in R and process them in R. There's other soil databases that are, some of them are more applicable to the US, maybe to North America, maybe some of them are applicable to the entire world. So it's not country specific. And they all have trade-offs as far as how accurate they are, what variables they report, what's the size in space that they represent. So what's the pixel size that they represent? They all have different differences in that respect. We have weather, so we're going to be using a database called Daymet, which is the best one we have access in the US. However, this data set here, so this data set, we're going to talk more about it, but for North America is the one that has the best spatial and temporal resolution. So spatial resolution is the pixel size that you get data from. So it's the finest scale that you get data from. Daymet, that is 1 by 1 kilometer pixel size. It sounds and it seems like a very large pixel, but it is the best that we can get for open source data in the US. And then it gives us data on weather on a daily scale since 1980. It's very, very comprehensive. However, if you go to other parts of the world, you may not have such a database even for weather. So we have other databases that may be at even coarser pixel sizes. But we're going to be using this one, Daymet, because it's the best we have access to in the US. You also have remote sensing data. So in this class, we're not going to be doing much remote sensing analysis. We do more of that in my other course. But we could get open source satellite imagery for a field and extract different things from that crop that's growing in a given year. We also have elevation data. So elevation in a field, in open fields in ag, is really important because differences in elevation in a field will dictate how water moves, how nutrient moves, what's the potential for soil erosion, things that really are impacting crop response. And many, many other potential variables. There are so many open source databases that we can leverage in ag. And the good thing about them is that a lot of them are free, right? So you don't have a cost to access them. You just have to know how to access them. So this is just one source of data that we can leverage for our projects. So why are we doing this in the first place? I guess the overall idea, regardless if you're thinking of weather data or if you're thinking about something else that may be more applicable to your research, is that we need so one of the strengths of machine learning models is that they leverage a lot of predictors, right? A lot of variables that you're going to give to a model, and that model will try to make a prediction based on those variables. Using open source data can really increase the amount of predictors you have in the model because you have access to a lot of variables. And even those variables that you retrieve from open source, you can further create other variables from those, which we're going to be doing on Thursday. So it's really important here for us to be able to access variables that you did not pay for or did not go to the field and collect, but they are still very relevant to what you're studying, and you have free access to them. So in today's exercise, we're going to explore a data set that is basically, well, I think I'm going to talk more about it in a second, but it's a cotton data set that has been collected across the US, southern regions, so all the way from Georgia and Florida to California over, I think, 41 years and in different places. So we have a lot of sites, a lot of years, and then in each one of those trials, we had cotton, some variables related to cotton collected, where one of them was cotton fiber quality. So if you're not aware of, if you have not worked with cotton before, cotton is a crop that we're interested in the yield, but also on the quality of the product. So imagine that, my shirt, I think this is a cotton shirt. So if you are paying for a cotton shirt or whatever it is that uses cotton that has a better fiber quality to that actual cotton that was harvested, that is valued more, you pay more for it, right? As customers, we pay more for cotton that has better fiber quality. So growers that grow cotton, of course, they're interested in yield, but they're also interested in producing a very high quality fiber from that crop because they get paid more because customers pay more for it. And so we're going to be looking into one cotton fiber quality parameter in this data set here today, and we'll talk a little bit more about it in a second. So our learning objectives here are to learn about and implement how to download and pre-process a spatial and temporal weather open source database. In this case, it's called Daymet. We're going to then pull that weather data from multiple sites and years to match all these trials that we have, the agronomic data collected, which was cotton fiber quality, in specific one of them. And then we're going to export this, all this weather data that we pulled, we're going to export this to file. So first, because we want to reuse it or continue to use it in the next exercise, but also because we don't want to have to be pulling the same data over and over if you don't have to. So you pull once from this open source database, you save it to file so we have access to it, and then we're going to further process it in the next class. All right, I guess any questions on that before we start coding? All right.
Dr. Bastos.
Yes.
So it's not a question about what you just said. It's just something from the previous class. Am I allowed to ask?
You're looking, sorry, I didn't get it. You're looking for the previous class?
No, like I have a question from the previous class.
Oh, okay. Okay, let me see. Sure, yeah, go ahead.
Sorry. So I know we talked about creating functions, but what if we've created a function before and we want to use it in another script? Does it work
That's a good
automatically?
question. So that is kind of like you're getting into the mode of even creating a package, perhaps, right? Because package is really that, is our functions that you create once and that you reutilize across different scripts, right? We're not going to get into package creation in this class, but so just to perhaps help you with that question specific. So Comfort is asking if we create a function and now you want to reutilize that custom made function in different scripts, is there an easy way to do that? So the least technological way of doing that is just copying and pasting that code of that function in every script that you needed, which is perhaps not the best. I would not really recommend it, because if at any point you want to expand the function to do more things, or maybe you want to change some arguments, whatever it is, if you change in one place and you want that change to be in all these scripts, you're going to have to basically copy and paste again a lot of times. So not reproducible. It is doable if it's something very simple, but it's not the best practice. The best practice would be for you to create. So I'm going to create here. We have not used a lot, just R scripts, right? We use, I guess, maybe in the first class, but we have not used that extensively. But really, R scripts, which is just a file type that ends in .r, are the files that people use to create functions, either for reutilizing internally, or even if you're publishing a package, it's going to be a .r script. So you can create a function here on this .r script and develop all the function, save this file, save this .r script, and then every time you want to load that function, you would basically come to your script and use a function called source. So let's say, let me just do a very quick, I'm not even going to write anything in here. I just want to save this to my code folder. So let me call this .r like example function, although it doesn't have a function in it. But just as you imagine that this would have your function here, and you save that. Whenever you want to reutilize that, you would come and use this source function, and you basically, I think I'm already on code. So you just call that R script. So if you do this, then whatever is in that R script is going to be loaded in your environment. And that way you can have one place where you develop this function, and every time you want to use it, you just call always from that same file. Because if at any point you want to make changes to that function, you just make the change in this .r file, and that change will always be reflected in every time you bring it in different scripts.
Okay, thank you. So is it fine to have multiple functions in the same file?
Yes.
Or just one function per file?
So if you are writing an R package, you would write a function per file. But if it's just like, so I have scripts that I basically just have a few functions that I use a lot that I custom made, and I just have them all in the same .r script. That's probably. And then the next step up from here would be to create an actual package, which then it's not as complicated as it sounds. It's a little bit more complicated than just doing the .r package or the .r function, the .r file. That's what I was trying to say. Yeah, but this would be maybe the initial step. And as you get more used to doing that, then you can look into how to create your own R package, even if it's not for open distribution. You don't want to like publish it, but you just want to use internally. Imagine that at some point you could have a collection of functions that you made and you called it, I don't know, like comfort package, whatever it is, right? You give it a name, you can install it. If you want to share it, you can share with other people that can install it and call that. So it's really, that would be the next step.
Thank you so much.
Thanks, Comfort. Awesome. Okay, so getting into today's exercise, back into it, we're gonna have to install a few packages here for this to work. If you are doing my other class, you may have some of these. If you're not doing my other class, you may not, if you have not worked with them before. But please go ahead and first install the package SF. What I would say is remove the comment and then just run this line of code. Do not run the whole chunk. Just run that install.packages SF and then comment it off once it's been installed and do one by one. So we're going to install SF, Daymet, remotes, and then USA boundaries and USA boundaries data. As you are installing on your side, I just want to let you know what these packages do. So today, because we're going to be working with geospatial data that was collected in different places across the US and also different years, we're going to be using some geospatial libraries in R. I'm not going to be talking too much about it because it's not the goal of this class. Again, if you're interested in geospatial analysis, that's all we do in my other class. So you can take that next semester if you wish, or next year if you're still here. And my recordings are all online, just like this course. So you can also check that way if you wish. But anyways, SF is going to be a package that we're going to be using to manipulate vector geospatial files. If you don't know what I'm talking about, do not worry. You just need to know that we're going to have points, that the location of those points are related to the geospatial coordinates of that point. And that's what we're going to be working with here using the package SF. If you No, I guess that's not the way I wanted to start the sentence. The next package here is going to be Daymet. So this package is an API that we have in R to access the database Daymet. So Daymet is a service on its own, and they have a API or a way for us to connect R to that website, to that database, and retrieve data through R. So without you having to go to the website, point and click and select and do all that, we're going to do that in R with R code. And this package Daymet is going to help us to do that. It's going to make that bridge between R and the Daymet database. The package remotes here is just a package that we're going to use to install packages that are not on CRAN. If you remember, CRAN is the repository of packages from R, kind of like the App Store of R. So what will happen is so let's say you develop a package, you want it to be available on CRAN, you submit it to CRAN, and it goes through a lot of checks, a lot of balances, making sure everything is correct. And once it goes through that process, then it's made available on CRAN. So every time we use install.packages, we're basically using CRAN as the source of that package for us. However, some people may not want to submit a package to CRAN, in which case you can still do a package, you can still make it available, just not through CRAN. What is very common is some people develop packages and they make them available on GitHub. So if you want to install a package from GitHub, you cannot use install.packages because install.packages feeds from CRAN, the official R package, App Store kind of analogy. So the package remotes here is going to allow us to use the function install_GitHub, which allows us to install packages that are only on GitHub. So then we're going to use this remotes package to install the packages USA boundaries and USA boundaries data. Both of these packages here, they're very useful because they have political boundaries for the US. So they have county boundaries, they have state boundaries. Really, really useful if you're working with data that you want to represent at that spatial scale. So this could be this doesn't, if you think of it, using county and state geopolitical boundaries is not something that's only applicable if you have field trials. It could also be applicable if you are collaborating with people in different universities and you want to show a map of that, or anytime you want to show something that changes in space, right? You can use these packages to get access to those, to the boundaries of those counties and states, if you wish. So I know sometimes, depending, I think in the past we have some people having issues installing USA boundaries and USA boundaries data. And I guess overall, I just want to check in if everyone has been able to install. No department having issues. Okay, someone else having issues? Okay.
Mine's just like getting and loading still.
Okay, which one is that?
I think it's the USA boundaries.
Okay. Aminder, could you check in with Madhuparna and help her out, please? Okay, online, anyone needing help? Anyone running into issues? I don't hear anything. So as Aminder is helping out a couple of students here in Athens, I'm gonna keep moving. If your console is working, meaning that if you ask to install a package and it is still processing, then you're not going to be able to run anything until that is done, but you can still type with me. Whenever we get to a point that it's going to be important for you to really type and run the code, I will check in again to make sure that you were able to catch up. All right, so again, I'm just helping a couple of students, but we're going to move on slowly here. So once you install all of them, again, remember to either comment off that install.packages or to just delete that if you wish, because you're not going to be needing that again. But do that on your side and then just leave the library functions active. And once you do that, we can just hit run on this chunk, and that's going to basically just load those packages for you. All right, so the first thing here is going to be for us to read in this database that I share with you, the cotton field data. We're going to read that and assign it to an object called field. So let's go ahead, give the assignment symbol. So if you go on the data folder where you should have moved this data into, is a cotton field data.csv. So comma separated value is the extension of this file. Because of that, we're going to be using the read underscore CSV function. So go ahead and do that, read CSV. And then you know how to specify the path, // going data, and then cotton field data. You can run that, so it brings in this data set into your environment, as I can see on mine. And let's just print it below so we take a quick look at what this is. So I will always look for things like what's the number of rows, what's the number of columns, and then talk a little bit about these columns here for us to be aware of it. So we have 698 rows. Each row is an observation. And we have 5 columns. These columns are year, so the year when the study was conducted. And this is a numerical, a double variable, so that's great. Sometimes year may come as, or really any numerical variable may be interpreted as character if you have a character in any cell of that column. So here it is already double, that's great. Arminder, could you help Model Partner as well? Model Partner right here. Yeah. Thank you. We have site. So this is basically just a description of where the study happened. So we have the city name or the town name and the state. That's the pattern we're having here. We have latitude and longitude. These are the 2 geospatial columns that we need to place anything in space. Imagine like when you're using, I don't know, you're sharing your location with someone on Google Maps or whatever, it is using longitude and latitude for that information. And then it has strength in grams per text. So this is basically one of the fiber qualities that cotton is tested on, is basically the strength of the fiber. So what this means is basically there is a test that checks for strength. But imagine that the stronger is the fiber, the more resistant it is to breakage. So a strong fiber is better. We want fibers to be strong, so they resist friction, they resist that breakage of the fiber. And the measure of that is grams per text. This is just a measure that the higher this number is, the stronger is the fiber. So we as customers, we pay more, even if we're not fully aware of this, but we pay more for cotton products that have better quality overall, and strength is one of those quality parameters that we're paying more for. So other things would be, for example, color, right? So we want something, we want the fiber to be very clean white. If it's like a fiber that's at harvest is kind of yellowish because it has suffered from maybe diseases or just deterioration of the fiber or other reasons, just weathering of the fiber, that fiber is going to be worth less because it's kind of yellowish, right? So color, strength, micronair or fineness of the fiber. There's a lot of different variables here. We're going to look into just one, which is going to be strength in grams per text. So as you're going to see when we start making a map here, this data set is comprised. So it was a study that was basically, it was a cotton variety trial study, meaning that they had many cotton varieties that were grown in all these different locations. And what I'm giving you here is just the average strength per location. So I'm basically not giving you the variety information here. We just want to try to predict the fiber strength at each location, regardless of the variety. But this is a USDA program board that's been going on for a long time, and we have access to data from 1980 to 2020, I think. Yes.
What did you say year was? Character. Because for me, it says INT. Do I need to change it?
Okay, so maybe you use read.csv instead of underscore CSV.
Yep.
Yeah, it's just so read underscore CSV comes from the one of the tidyverse packages. So when you read using read underscore CSV, it comes as a tibble. If you use read.csv, it's base R and it comes as a data frame. So there's some differences. It shouldn't really matter if R interprets this column as double or integer, but it's just because of that difference of the function. Yeah. All right, so we talked about what was the goal of this study was basically to measure, well, many things. The one that we're interested in this exercise was cotton fiber strength at the end of the season in each one of these sites and years. And again, these are the columns that we have. So let's do, as always, some quick EDA. Always do EDA, check on your data. So here we have so we get a fiscal summary for year. We see that is ranging from 1980 to 2020. So we have data set over 41 years. We have latitude and longitude here. This is something that if you're not used to working with geospatial data, it may not be obvious to you. But this data set here is only within the US, meaning that you would have some expectations of how your latitude and how your longitude values would be. So for example, latitude, it would have to be positive number because we are above the equator. And longitude would have to be a negative number because we are to the west of the Greenwich line. So, again, checking here can help you because sometimes if you make a map of this and maybe one of the data points is in Europe, then you realize, okay, I know there's no studies in this data set coming from Europe, so maybe it was a data entry error. Maybe when the person was entering the data, they forgot to put the minus here. So just one way, another quick way that we use summary to check our variables. And then strength here, we can see that's ranging from about 20 to 38 grams per text. That's how much variability we have in this data set as far as our variable of interest. And now that I said that, I just want to take a quick moment here to say strength in grams per text is our predicted variable, is what we're trying to predict, make models to predict this variable. So now our goal in this exercise is going to be to bring in weather data as predictor variables to append to this data set so we can start having some variables that we can use to predict strength. All right, so now let's just do a few things here and check how many unique years we have. There's a couple of different ways we can do that, but let me ask if anyone has any idea of what function we'd use here to check how many unique years we have. So I want to know exactly how many years we have in this data set. Because here on the summary, I know that's ranging from 1980 to 2020, but that doesn't mean that we have every single year in between them. So if I want to just know how many unique years I have in this data set, how would you do that?
You could use the function unique.
Yes. So Shay is saying here that we can use the function unique. We can do that. So we can put here the data set is named field, and then we would just ask for the $sign year, right? So we could do that. It gives us a list here. But that's one of the ways we could check it, right? So we can see here that your last element 2020 is in the position 41. So this is how we could do it. I think we could perhaps pipe this into a length. Maybe let's try that. Yeah, so we can pipe this into length. That would give us the exact number, so we don't have to just guess. Yeah, but that's a good approach. All right, so 41 years in this data set. Now let's check how many unique sites we have in this data set. And I do want to show you a different function just to add variability to our understanding that in programming, there's probably more than 2 or 3 ways you can do the same thing. There's no right or wrong as long as you can get your answer. So we could have used also the function, well, let me begin with the data set so I can pipe this in. So in the field, there is a function in, I think, dplyr called distinct, which is very similar to what unique does. And we just say the column name here. So distinct sites. It returns us a tibble, so a data frame that we can really see there are 65 rows, meaning there's 65 sites. We could have also, let's try if I type this into length, if that would length of site, if that would give a number to us. Oh. That actually did not work. What if I just do length? That didn't work. What if I do n row? Maybe that's what it's trying to get. Yeah, so n row would have worked. So how many rows we have in this data set? So 65 unique sites. So 65 unique sites across 41 unique years for a total of 698 side year combinations on this data set. All right, so now I wanted to check the statistical distribution of fiber strength as a plot. How would you do that? Jonathan, what do you think? Don't know? Zach?
Ye-
Oh, I'll go online just a sec. So it is going to be a ggplot, right? So I want to make a plot. It's going to be a ggplot. So I'll give you all that. Okay, let me keep helping you all. So data is, we know is going to be field. That's the object that we have our data in. So let me ask specifically, Zach, what would be the geom that you would use to check a statistical distribution that we've used in class already?
That's an easy question. Yes. Not geometry. No.
So geom smooth is not going to be it. Geom smooth is basically to add a trend line, right? So if we want to check the statistical distribution, well, there's a few ways, but one that we use more in this class, a few geoms, but one that I'm looking for specifically. I think online somebody was going to say something.
Oh,
It could have been a box plot. That is an acceptable answer, but I'm looking for something that we used before.
Density.
Histogram.
Geom density. Okay, geom. All right. Well, thanks. A lot of people were giving ideas here. So just to tell you, it could have been box plots, it could have been density, it could have been histogram, could be all those. I normally prefer density for some specific reason, so that's what we're going to use, and I'll tell you why in a second here. Let's use geom density. If you remember geom density, we need to give on the AES one variable, which is the X variable, which is the one that we're interested in getting the density of. We don't need a Y variable because the Y is calculated by geom density. So the variable that we want to look into is called strength underscore grams per tex. So if you run, let me just make this a little bit shorter. So if you run that, this is what we're going to see. So a couple of thoughts here. We could have used box plots. It would be a little bit different though, because I think, well, maybe let's just quickly try to change. If we use box plots. Okay, so it would have actually worked just by changing the geom. I normally prefer density because I think that there's a really nice blog post. I think it's on, I don't know, Stack Overflow maybe, that shows like the same looking box plots and then their density plots below them, and how you can get the same box plots are looking very similar to each other, when the underlying density is very different. So that's why I tend to prefer density plots because they give us more information, but box plots would also be a good one here. You could have used geom histogram. So geom histogram is pretty similar to a geom density. I normally think of geom density as kind of the outline of this histogram. But it could have also been, you could have also used a histogram. I'm just going to keep with geom density. And I think I don't remember if in this class we used, but so geom density gives you that outline, but you don't really know where the points exist. So you can always add here as well, geom rug. I'm going to have to say yes, x equals strength as well. Strength gtex. So geomrug adds a vertical bar on the bottom of this density to indicate where each observation is happening. So that maybe gives you a little bit more information on this geom density. So as we already saw on the table, you have a question? Okay, I thought you were ready to ask a question. As we already saw on the summary table, so it looks like the mean is probably around 30, right? So if we go back here, the mean is, 32, right? Mean and median around 32. So, sorry, I'm looking the wrong column, actually, this column. So the mean and median of strength are around 30. So, this statistical summary gives you a quick way of checking your entire data set and see if anything is making sense. Whereas looking at the actual distribution helps you to understand the shape of that distribution, right? So it gives you an extra information rather than just looking at a summary table. All right. Let's see. Okay, so on this next chunk here, although I just realized I gave you no comments to tell you what we're going to do, but what I want to do next is to create a map of the US and basically add on this map the information of where our points are. So we see now the spatial distribution, not the statistical distribution, but the spatial distribution of data set that we're using. So for that, we're going to be using a couple of packages that we just installed. So the first thing here is going to be for us to get a shape. Well, let me not use words that I don't need to use. To get the boundaries of the states in the US. That's the first thing we want to do here so we can make a map of that. So let's go ahead and call this object states. On that USA boundaries package, there is a function called US underscore states. If you just run this and you print this object states, so this is a simple feature or SF object. Again, if you're not used with geospatial data, don't worry, and we're not going to get into the details of that in this class, but all you have to know is that this object is a geospatial object in R, and we're going to be making a map of that, therefore. So we have a lot of columns here. So some of the ones that we're interested in is name. So we have all 51 states, I guess. In here, we have, so the name of the states, we have more information about each one of those states, but then we have this column called geometry, which is a special type of column that applies to geospatial data, that it just places those states in the right place in relation to each other and in relation to the globe as well. Now, okay, so maybe for now, we can leave that states like that. Let's now create a map of this. So we're going to use ggplot as well. Add a plus, you don't have to specify anything at the ggplot level. We're going to use a new geom that in this class we had not used yet. That's called geom underscore SF. So this geom underscore SF is only used to plot SF objects, which the one that we just created above the states object is an SF object. So we're just going to say data equals states. If you run that, this is what we see. So we have a map of all the US states and territories, which, great, they're all there. However, there are some of them that we really don't need because this is a map, it is respecting the spatial location, right? So we have Alaska here, we have Hawaii, we have Puerto Rico and Virgin Islands, perhaps, or maybe this is still Alaska. Yeah, this is still Alaska. Virgin Islands is not there. But so we have these other states that really we don't have data in any of those. We don't have data in Alaska, Hawaii, or Puerto Rico. So we're just going to remove those from the states object. So our map is just for the 50 conterminous states in the US. So for that, you come back to the states here. Well, let me just print states first and then ask if somebody can help me on how would you do this? So if I want to remove here Hawaii, Alaska, and Puerto Rico, we have a couple, maybe even a few columns that we can use for that. Can somebody help me here with the code? What would you do here?
Select, then specify the column.
So select is acting on columns, right? So I want to select a column, the whole column. What we want to do is actually not on the columns. We want to work in the rows. We want to remove some rows that where states are equal to those three that we want to remove. So the function is going to
I think it's filter. I think we should use filter.
filter, right? Yes, I agree. So remember that select works on columns, filter works on rows. So let's use filter. And now I'm going to give the rest here just to avoid a lot of confusion. But so there's in this data set here states there are 52 rows. We want to exclude 3. So it's easier to say let's exclude 3 rather than let's keep 48, right? However, the way to do that in filter is going to be a little bit interesting. So the first thing I want to tell you is let's say that we only wanted to keep those 3. Let's think about that first, and then we're going to invert that thought. So I want to use here, we could use different columns, but just to help us with typing, there is a column that is for states abbreviations. I'm going to use that column to filter. You could use the name column. You could use, a state name column as well. There's a few options that we could use here, but I want to use this state abbreviation because it's going to be shorter for us to type. Every time I want to keep more than one value, we have to use the percent in percent. We've seen this before, maybe not a lot of times, so maybe you don't remember, but we've seen this before. And then we're going to use the C function to give which ones I want to, in this case, keep. So the acronym or the abbreviation for the ones we want to, right now in the code, keep, but in the end to remove is going to be PR for Puerto Rico, AK for Alaska, and HI for Hawaii. So if we run this piece of code and then you print what states look like, you're going to have only those 3. However, we want the invert of that. We want those to be removed, not to be kept. The way to do that in R is, I'm just going to give a couple of spaces just so it's easier for you to see. So this is our statement, right? This is what we're specifying that we want to keep. We basically wrap this statement around parentheses, and we come in front of that first parentheses and add an exclamation point. This basically negates what you're saying. It basically says what you're asking, but the opposite. That's what adding that exclamation point does. The alternative here would be for you to say to only keep all the 48 remaining states, which would be a lot of work, unnecessary. So we're saying keep these 3, but then invert that logic. That's what we're saying with this exclamation point. So if you run that and now you print states, we should have 49. Oh yeah, we have 52 starting. So we have 49 now that we remove 3. And now if you plot that, if you run again the ggplot, you should see a map of the 49 conterminous US states. Okay, So now we have a map of the US. Now we need to place our data in that map, in space, right? There's a couple ways we could do this. I'm gonna go on the easier one because again, this is not a geospatial class, so I don't want to spend a lot of time on that. So let's add a plus here. Now we're gonna use a geom point. So I want to have a point on each location where we have a trial. The data set is gonna be the field data set. So this is the one that we imported, is a different data set. And then here on the aesthetics, we have to say what goes on X, what goes on Y. So let me print field here just for us to look into it. What should go on X, what should go on Y? Which columns? Ruben, what do you think?
Dr. West.
I'll go online just a sec. Just let me check here.
No.
Okay, latitude and longitude would be going on X and Y, right? I think Omar had a question or a thought.
Yeah, I was about to say the same. Latitude and longitude.
Perfect. So I'm not gonna ask you all specifically which one goes where because I know this can be very confusing to think of what is X, what is Y when you're talking about longitude and latitude. So I'm just gonna give that to you. So X is longitude and Y is latitude. Those are our columns. So if you run this, now we get a point on each place, on each site where we had at least 1 year of trial, right? So we can really see here that this database is running all the way from east to west coast. And because of this, weather differences are so important because you have a huge weather gradient going from east to west coast. And we would hypothesize that weather, which is what the crop that is growing out in the field is actually seeing and responding to, would be such an important variable for us to have in this data set. Okay, any questions or thoughts about this?
Dr. Bastos,
Yes.
please, could you quickly go through what the percentage in the filter column means?
Yes, so
Yeah.
we saw this maybe 1 or 2 times before, but we have not seen frequently enough for y'all to remember. So if I wanted to filter just one state, I would use equal sign. But because we're filtering more than one, in this case 3, if you give an equal sign, it's not going to work. So we need to use the percent in percent, which is basically the equivalent of the equal sign, but is applicable when you have more than one condition.
Thank you.
Thanks, Comfort. Any other questions or thoughts? Okay, so I think I want to give you a quick break because it's been an hour already. So I think this is a good 5-minute break point for us to have that break. So let me put here 5 minutes on the clock and then we'll come back to start working with Daymet and pulling weather data from that. All right, our time is up, so let's resume here. Again, if you're online, make sure to turn on your camera once you return. Okay, so now let's talk about Daymet. I already told you a little bit about it. We're just going to go through it again. So Daymet is an open source weather database developed by NASA. If you want to explore their database or their website, I left the link in there for you. I'm not going to do that, but you can do that on your site if you wish. So Daymet provides us long-term, continuous, and gridded estimates of daily weather and climatology variables by interpolating and extrapolating ground-based observations through statistical modeling techniques. So if you work in ag, you probably are familiar that the best weather data you can get is if you have a weather station in that specific field. That's the best weather data you can get. The next best, if you don't have a weather station in that field, is going to be for you to use the weather station network that different states across the US have. We have a great network here in Georgia. I think we have about, well, I don't remember the number now, but maybe about 90 or over 90 weather stations in Georgia that are part of this, the Georgia Weather Network. That's a really good number. But some of the trials that we have done in the past, if we go to any specific field in Georgia that we're working with, we could be right next to a weather station as part of that network. We could be up to 25 miles away from the nearest weather station. So if you're really far from an actual weather station, there's going to be a point that is going to be better for you to use open source gridded data like Daymet. Also, something that Daymet is really helpful with is you have an archive. You can go all the way back to 1980 and get daily weather data variables for anywhere in North America in this case. So the fact that you have an archive that's a continuous gridded database make it a really, really strong database if you don't have weather data. So again, Daymet is not going to be the most accurate if you compare to having a weather station on that field. But if you didn't, and there's nothing you can do because it has already happened, it's in the past, Daymet is a great source for weather. So it is some of the data characteristics of Daymet. It is the extent of it is just North America, so US, Canada, and Mexico. It has a spatial resolution or a pixel size of 1 kilometer. So each 1 kilometer cell in space, you have a different weather data available potentially. It has a daily temporal resolution, meaning that you have new data for each day. You have that weather data available across the US or North America. And it starts all the way in 1980 and goes to present day. So if you go today on Daymet website, you can probably pull data from yesterday. So it's updated daily. And includes some very important variables in agriculture. So day length, precipitation, shortwave radiation, snow water equivalent, maximum and minimum temperature, air temperature, and water vapor pressure. We're not going to be talking too much about the effect all this has in crops, but maybe the one that's easiest to think if you're not used to working with crops is that we need to have a certain level of precipitation and or irrigation to grow a crop. So that's a very important variable. Temperature is also really important because if it's way too hot for way too long, crops start suffering. If it is cold too soon, it can also kill crops when we're not intending for them to be killed by temperature. So these variables all of them impact how crops respond to the environment, but those temperature and precipitation are normally the most important ones. So Daymet provides an application programming interface or API that allows us to connect to that database through different ways. It doesn't have to be through R, it could be Python, it could be other ways. In R, there is a package called Daymeter, the one that you installed, that helps us to make that bridge through the API from R to Daymet. And the main function that we're going to be using to call that API is called download Daymet. And I want us to look into the documentation of this function just so we understand a little bit better. So if you just run that help download Daymet, it's going to launch for us documentation on the right. So function to download a single location Daymet data. These are the inputs that it requires. So we need to have a latitude, we need to have a longitude, we need to have the beginning of the year and the end of the year, which really, if you just give the beginning and end as the same year, it's just going to give you all days from January 1st to December 31st. And then it has some other ways here or other arguments just to how things are parsed. So one that we're going to be using here, I think, is simplify, but we'll talk about that later. I guess as far as what Daymet needs from us so we can get weather data is basically latitude, which we have, longitude, which we also have, start and end of the year, we also have it. So we have all the data that Daymet requires for us to download weather data. So the first thing I want to do here is for us to pull weather data for one site and 1 year only. So the first one in our data sets. Let's go ahead and do that just so we understand how this data looks like for one site and 1 year. So we can print here field just so we remember, have a refresher on the name of the columns. If you go on this object Daymet1, we're going to call that. So this is going to be the object that we're going to store the weather data for one site year. So give it the assignment symbol. We're going to call this function download Daymet, which is the one that we just did above. So it has an argument for site. It's just the name that you want to give that site. So what we're going to be doing here is we're going to call field $site. So really, I want to give this first row here to Daymet, to this function. So for us to say this site here, we use field $site. So this first site, and then we use double brackets 1. So if you just print field $site, double bracket 1, it basically just returns you that first site. Okay, so this is what I want to give as a site name. And again, the download Daymet function will work if you don't give a name, but we still want to give a name so we know what is that site, what's the name of that site. The next argument we need to give is going to be lat, so latitude. I'm going to print field here again. So we want to give that first latitude value on the first row. So very the same way, we're going to do field $lat, double brackets 1. If you just print field lat double bracket 1, you get the latitude of that first row. That's what we're given, right? We're just focusing on that first row and giving the information that the function needs. The next thing that Daymet needs is the longitude. So we say long, that's going to be equals to field $long, double bracket 1 to get that longitude value. So on the start and end, if you just give the same year, both as the start and as the end, that's going to give you, again, data from January 1st to December 31st, which is what we want. So on the start and end, we're going to give 1980, but I don't want to type 1980. I want us to use the same notation we've been using up until now. So field $year, double brackets 1, and then end the same way. And equals field $year, double brackets 1. So that year that we're specifying is 1980, right? Is that on the first row? That's the bracket sign 1. And then there's an argument for simplify. The default is false. I want to set it to true, just so the data comes a little bit more tidyverse friendly. That's it. All right, so if you go ahead and run this Daymet1, it probably shows a message to you saying downloading Daymet data for Altus, Oklahoma at the latitude and longitude, and then it says done. It said done pretty fast because we're just pulling for one site, so it was pretty fast. Now let's print this Daymet1 and just look into what's in it. Okay, so this object Daymet1, which is daily weather data for one site and 1 year only, has 2,555 rows. How come? What's going on here is, so we have a column site, which is the same name all the way down. We have the column tile, which is just the tile from Daymet that this site was in that tile. Imagine you have a pixel, right? It's just the pixel number of where Altus, Oklahoma is in. We have latitude and longitude, and also give us altitude. So we didn't, that's something that's coming from Daymet, is the altitude of that site. The year is the same all the way down if you were to look into it. And then we have a few columns, a couple of columns here that I want to talk about. So Y day is the day of year that ranges from 1 to 365, right? So that's the day of the year on this data set. But then it has a column here for measurement. So measurement column is going to have a lot of different values. So let me just try to get to the end of the 365. Let's see if that allows me to get there. Okay, so you notice here that 365, the variable all the way up until here was day length in seconds per day, seconds per day. And then it starts again on day of year 1 with a new variable. And then it has a column for value. So this, you may be realizing, it looks like, imagine if you have a data frame that you had each weather variable as a column, it looks like this is the product of a pivot longer, right? You bring from wide to long. And so you have all the measurement names under measurement and all the values under value. So what I want to do for us to be able to see this a little bit better is to actually undo that pivot longer, which comes by default from Daymet. Let's do that here on this next chunk. So what function do we need here? Pivot longer, right? Or is it? We want to undo the pivot longer. So what would be the opposite? Wider, right? So we want pivot wider. So let's do pivot wider here. So there's a couple of arguments that we're gonna give here. So one is the names from, so this is what column has the current names that will become columns after we do wider. So the name of that column is measurement. And then there is another argument for values from, which is the column that has the current values, which is called value. Oops. All right, so if we run this, now we have 365 rows. Now this makes more sense, right? We have one row for each day of the year, and then all of our weather variables now became their own columns. So we have day length, we have precipitation, solar radiation, snow water equivalents, maximum temperature of the air, minimum temperature of the air, and then vapor pressure deficit. So all of our columns now are, all of our weather data are in different columns, right? And each row is one day of the year. So if you were to go all the way to the last page here, that would end on 365. Does this make sense? Because I know that maybe we use more pivot longer than wider. I guess, does this make sense for you visualizing and understanding what's going on? All right. Perfect. All right, so we just pulled daily weather data for Altus, Oklahoma in 1980. Pretty cool, right? You just got this data in this chunk. Pretty simple. Now, we just need to do the same thing for 697 other site years. Cool. However, you are pretty good at iteration at this point. So we're not going to have to type that 697 times. We're going to use some iteration tools. So we're going to use the function map in this case, or maybe not map itself. We're going to use the map family of functions to do this. Again, this could be done as well with a for loop. This could be done with any of the apply family of functions if you're using those. I'm just going to be showing you the one that that at least I have a preference for, but you can do whatever you want on your projects, of course. All right, so let's come here on this next chunk. This is, we're gonna sign, so right now our next step is gonna be to download weather data for 698 site years, all at once, all in one code, and have that all saved to Daymet all. So let's start with that. We're gonna start here with our data frame, which is field. And okay, so let me ask you some questions before I start giving you the answers. So one thing that maybe, let me just print for you here and show you. So now, although I've showed you in class how to use a group by and nest to create groups of data set and then do something with them. In this case here, I mean, we could do it if we wanted, but because we want weather data for each site and year, which means each row of this data set, if we did a group by site and year and nested, it would be the same as not doing it because it was still going to have 698 rows. So it wouldn't really change much. So we really don't have to do the group by nest in this case because we want data for each individual row. So with that, we're going to basically not need those steps of group by nest. We can get straight into the mutate and use one of the map functions to work here. So I want to call this column. So imagine that we're going to have a column where in each cell of that column is going to be a data set that contains all the weather data for that site and that year. So basically all this from this site here is going to be in one cell under this column weather that we're going to create now. So I want to call that weather. Let me ask this question. Should we use map, map2, or pmap, and why? Pmap, right? Okay, everybody, at least here in Athens, said pmap, because we need to pass this function year, site, longitude, and latitude, 4 inputs that's going to be iterating over, right? So yes, we need to use pmap. Let's go ahead and use pmap. So the syntax of pmap is a little bit different. So I want to, so this is not something I would expect you to memorize. It's something I don't memorize. I always ask, Google or something. Yeah.
But it's related to pmap. Can you still just use pmap for like 2 variables, or would it be better to use map 2?
You could use pmap for 2 variables. It's just, so pmap has a couple more extra lines of code to create the structure that for it to work. So if you just have 2 map, so if you only have 2 iterating variables, map2 is going to be simpler, right, to code, but you can still use pmap. There's nothing that's going to keep you from that. All right, so if you remember the structure that pmap requires, we need to specify a list of how we want to refer to those columns. So I want to say .y equals to year. So that's the placeholder that we're going to use. Give it a comma. I want to call .site equals to site. And again, the .y and .site are what I am naming them. I could name them anything. It could be X, Y, Z. It could be A, B, C. Really, the important thing is that after the equal sign is where you give the actual column name in your data, right? So we have a column called year. We have a column called site. So we're also going to do a .lat. That's going to be equals to the lat column, and a .long. It's going to be equals to the long column. So after you specify this, let me bring here. So this, the first closing parentheses after long is the one that's closing that list function. And you can kind of check that by, like, if you just navigate around it, it's highlighting that parentheses. So it's closing that. So once you close that, give it a comma, break line just to make it easier for you to see. We need to call this function called function, where we basically just start those placeholder names. So .y, comma, .site, comma, .lat, comma, .long. So we just kind of start that. After you close the parentheses of that function, break line one more time just to help you here to read your code. This is where we call the function. So the function we're going to actually use. So it's called download Daymet. I'm seeing that there is a download Daymet batch, which I think this function is new. Last time that I taught this, I don't remember this function being there. So maybe Daymet already developed a new function, or Daymatter package, develop a new function that helps you to download in batches. We're going to ignore that for now, because we're going to see how we can do our own batch download instead. So download Daymet is the function that we used before on the previous chunk. I want to come inside the function and break line again, just to make it easier for us to read this function. And so it has the argument site, right? So we're going to say site equals to dot site. That's our placeholder name that we specified there. It has the argument for let. We're going to say it equals to dot let. It has the argument for long, which is going to be equals to dot long. It has the argument for start, which is going to be equals to dot year. Or sorry, dot y, that's how we call this, dot y. It has the argument for end, which is going to be equals to dot y as well. So notice we're given the same year as the start and end. That's how the function understands it. We're going to change that simplify to be equals to true. So notice that the true here is not something that we're iterating differently. It's just always true for all the runs of this function. And then finally, I want to ask for it. There's an argument for silent. I want to say equals to true, because that's going to inhibit progress messages. So it's just going to make the output a little bit less convoluted as it is downloading 698 times. All right. So this parentheses here is closing that Daymet download, or download Daymet. Right, I'm just going to bring here so we can now see it better. And there's one quick step here that I want to do just for us to like one wrangling step that's going to make the data look a little bit better once it comes through. It's something that I only discovered the issue after running. And because I don't want you to download 698 site years and then go back, fix, and rerun it, I'm just going to give you the solution before you see the problem. But it's going to be a simple solution. So what happens is our incoming data set has a column called year. And the data set that Daymet gives us also has a column called year and site. Sorry, both year and site, not just year. So what happens is when Daymet gives you back site and year, is going to have two columns for year, two columns for sites. One that you have already, one that's coming from Daymet. So I just want to basically help for that confusion to not happen. So right after that download Daymet and a pipe, and we're going to use a rename function. I want to rename so coming from Daymet's going to give you a column called year, but I want to rename this to dot year so it does not conflict with our current year column. And the same thing for sites. So you say dot site is the new name, and then site is the current name from Daymet that we want to change. Okay, so if you got all of your commas and function, parentheses, opening, closing parentheses, everything right, if you did not forget any comma here. So a good thing to just tell you here, because I know you're just typing along with me, but if you forgot something and the code knows it, you may be seeing an X in any of these lines of code, like a red X, like this. So I just removed the comma here from the dot Y, and then it gives me some indication there's something going wrong. So if you see that on your code, go on that line and inspect it. You may be missing a comma, you may be missing a closing parentheses, whatever it may be. If everything looks right, and if you come all the way here on Daymet and just run it, it's going to start downloading 698 site years of data. Because we asked for silent equals true is not telling us 698 times that something's being downloaded, but it is. It's probably running on your side. It's going to take a moment here just to download all the weather data. And so we're just going to wait for that to go through. But once it goes through, then we're going to take a look and see how that looks like. I guess while this is running, at least on my side, anybody has any questions or thoughts that you would like to ask?
Dr. Bestos, I have something.
I'll go with you, Charles, just in a second. Yes, is that Omar?
Yes. Yeah, I was wondering about the assignment that I brought up yesterday to you. So are we gonna get any extension for the deadline or it's due at the same time?
So the assignment is still due on the date that it was advertised to be due, which is today.
Yeah, but it was not visible till yesterday.
Well, the due date was on the script. I guess I just didn't make it. I just didn't forgot to make it visible on ELC, but the day was the same as we talked about in class.
Okay.
Yeah, so what happened is, so Omar sent me an email yesterday asking for the assignment, so the iteration assignment. I had forgotten to make it visible to you all, so you maybe were not seeing the deadline being today. But we are still talked about the deadline in class, so the date did not change. It's just the fact that it was not visible yet on ELC. Has it finished running for anyone? Still going? Okay, because I know sometimes my computer goes a little bit slowlier because of Zoom. Sorry, can you say that again? I still could not quite hear you. Go through the rename. Okay, yeah. So what you're gonna see, so Charles is asking for us to go through the rename, to explain the rename here. So the rename is something that, again, I realized it was necessary after running everything once, but I didn't, and normally I would allow us to go through those problems and find the challenge and then fix them, so you understand the logic. But in this case here, I'm giving you the answer before the challenge is happening, just because, as you see, I don't want you to spend a lot of time downloading just to have to download again. So basically what happens here is the download Daymet function. I think I can still show you that here. So this is the output from the download Daymet, right? The one that we just did for one site. So it gives you a column called site, and it gives you a column called year on the Daymet itself. The thing is, once this PMAP goes through, each one of those data sets that we just pull for one site is going to be in one cell, right? Of that data, of that column. And when we unnested to bring all that into the main data frame, you're going to have the columns site and year from your original data frame, and also site and year from Daymet. So there's going to be a conflict there. Yeah. So that's why we're basically renaming what Daymet is giving you to .year and .site. So in the end, when you unnest it, you're still going to have your site and year columns and .site and .year from Daymet. Yeah, Charles. Okay, so this is taking a little bit longer than I remembered, and we only have 3 more minutes. So I think we're basically going to have to, get your attendance. So I think, Arminder, have you had a chance to? Okay, thanks. So Arminder already opened the attendance. You can claim your attendance. What I would say is, if you can, I don't think this takes a lot longer, maybe, I don't know, 5 minutes or so. If you have the time that you can leave this running, I would say wait for it and then save your script. Do not close this RStudio window. You want to have this object there for Thursday, so you don't have to rerun this before class on Thursday. Yeah, so let's do that. So once this goes through for you, just save your script. Do not close this RStudio window, just minimize it. And then we're gonna keep going on Thursday. We're just gonna, after this is downloaded, we'll probably take 20 minutes to finish this exercise. And then we're gonna do the next exercise, which is gonna be feature engineering. So let me tell you a little bit about that. So feature engineering is basically a process in data science that we create new variables from the ones that we have, right? So as we are seeing here, we have all these weather variables coming from Daymet on a daily scale. Working with weather data on a daily scale can be really tricky, because imagine that you may have, let's say, we talked about precipitation being a very important variable, like, right? So how many times in 40 years you get a given amount of precipitation in a given day? It's going to be really difficult to make sense of that, right? For a model to tell you, well, on May 21st, if precipitation is more than this, then your prediction is that, because it's so variable on a daily scale. So what we're going to do is we're going to define windows of time for which we're going to be extracting this or summarizing this daily weather data. I believe our exercise, we're going to be using monthly. So we're going to take the month and take an average temperature for each of the months, and then a cumulative precipitation for each one of the months. I think that's what we're going to do. But that window of time could be really anything. It could be on a weekly basis. It could be on an yearly basis. It could be perhaps around specific crop growth stages. So if you are working with crops, you may be aware that crops are more affected by drought or lack of water in certain very specific growth stages. So if you can have that information, maybe you can create growth stage windows instead of just monthly, that is arbitrary. So anyways, feature engineering, we're going to feature engineer a lot of new variables from the ones that we're getting here from Daymet. That's going to be the topic of the next class period, which will require us to have this daily weather already downloaded as an object. All right, it just finished for me. But so once it finishes for you, just make sure you don't close this RStudio window so you don't have to wait for 10 minutes next class to download. All right, so I think that's all I had. If you claim your attendance, then you're good to go. Otherwise, I'm going to stick around for a couple minutes if anyone has any questions.